So.
About the neutron EDM search at PSI. The neutron EDM search at PSI. Philippe has been the spokesman of the collaboration for 4 years, I've just learned. And I'm pretty sure he's going to give us a great overview about the experimental results that are going to come, hopefully very soon, about neutron EDM at PSI. Thanks, Philippe. Thanks for coming.
Yes, thank you, Andrea. Thank you, Andreas, and our other organizers for having me here, inviting me to this beautiful place. And it's been already quite some fun to participate here. The plan of today's talk is to present the, oops, what do I have here? The chat. So to present the current most stringent limit we have measured in the collaboration of about 14 institutions at the Paul Scherrer Institute. I will go into details what we did before we actually started measurement, what we have optimized, then the measurement, the analysis, and I will conclude then what has happened since we stopped the measurement, did the analysis, and in parallel we start to set up the new experiment. Kent already showed you the motivation why to measure the neutron EDM. Here's my little kind of sketch why it's interesting, because it's CP violating. And if you look at spin 1/2 particle in a magnetic field, we all know that's the Siemens splitting, and you can measure the Siemens splitting as the Larmor frequency between the two levels. And if you would put a spin 1/2 particle where the electric dipole moment is coupling to the electric field, you would get the same sort of splitting. However, if you then apply a time reversal transformation, you will see that the spin up state will flip over in the case of the electric dipole moment, where in the magnetic dipole moment doesn't change. So you can distinguish the two cases. And because of distinguishing the two cases, the Hamiltonian is violated, and that's the CP or time violation. And if you then assume the classical theorem for CPT conversation, it's also a CP violation. And you also heard in that workshop already why it's interesting. It's because it's an essential part in the baryon asymmetry of the universe. It arises somehow naturally in many complex phases of beyond standard model physics scenarios. And there's this strong CP problem, which would give rise in the standard model some sort of CP violation. And in particular, the neutron or the proton would be susceptible for this sort of CP violation. And whenever you have such a CP violation, there's a good chance that you would or should see it in an electric dipole moment. Oops, we are, oh, it's changing differently. So you know this plot somehow also from Kent. Maybe I point two things out. There's actually one more result in the electric dipole moment searches, which has been done before even anyone started to measure the electric dipole moment of the neutron. And that was also done by Ramsey. And they actually didn't do the experiment. They looked at data where they scattered neutrons from lead. And from the scattering data, they deduced here a value which is below 10 to the minus 18. Then the one which I'm talking a lot about is this one, is the latest. You see there are many other electric dipole moment searches. They are susceptible to all sorts of different ways how CP violation could enter into the game. And so in the end, this is a complementarity and a field which is quite fascinating by its complementarity and its handle on some sorts of beyond standard model physics. Another thing I want to advocate here is up here is the muon EDM, and that's, so to say, my new hobby. I'm trying to measure that much better than that here, somewhere down here. It's in the 20, so I didn't put the plot where I want to go, but it would be much, much better if it works out in the end. And also there is something interesting. I forgot that on the plot, there's also the second ever measurement of an electric dipole moment was also the muon EDM. So I kind of go back to the roots now. On the right side, I put together what you would expect here for the neutron when you would have the standard model, so to say, background. That's essentially the CKM background, and we are about 10 to the 6 orders of magnitude away. If you look at the same for the electron, where it's about 10 to the minus 44, it's much more headroom they still have. And so if you look at the space of beyond standard model physics before you come into the background of standard model, we are actually the closest with the Mercury. And now I focus on my talk. How do we measure this energy splitting? So this energy splitting is essentially a measurement of the Larmor frequency or the electric frequency between these two levels. And you superpose this spin up and spin down state, and then you have this precession. Now, if you would put everything together, you would expect a precession which is essentially 53 nanohertz, which relates to something like a turn in a year of the spin. And so it's kind of hard to measure that because you have a very big systematic effect. And that's the classical Larmor frequency. So even if you have the best ever built magnetic shielded room, so that means there's no magnetic field inside. So your field is something on the level of a few picotesla. Then you still get something like a precession of a millihertz or 0.1 millihertz. So this is a turn in 2.5 hours. So you would have to control this very low field very precisely. And so it's easier actually not to do that, but to go to the scenario where you apply a known magnetic field, which you can control much better because you need currents to produce the magnetic fields. And if you would go to these very low magnetic fields, the currents would be extremely tiny and you would be in the noise of your power supplies. So you actually go to something which is a defined magnetic field. In our case, this is 1 microtesla, so it's not 0. Then you apply in one case a positive electric field, you measure the level splitting, you do the same thing again or at the same time with the inverted, where's my pointer? Here's my pointer. With the inverted electric field, and then you have these two measurements of this level splitting, and you can deduce the electric dipole moment from the difference. Assuming, and that's the entire name of the game, measuring an electric dipole moment, is to control that this part delta B is vanishing. If it's not vanishing, you always measure something which is related to magnetic field. And so essentially, we formulate in our paper all systematics as something which generates a magnetic field as a function of the electric field. This you also have seen already, it's Ramsey's method of oscillatory separated magnetic fields. The idea is that you have the spin aligned, prepared in the first stage. You apply from a known high precision clock a pi-half pulse, which tilts the spin into the plane. Then you get the signal out again. You have a free precession area. You get in the same with a known phase difference or exactly in phase, these two. So we assume now in phase scenario. Then it tilts the spin again to the bottom. And in the end, you get something which is a interference pattern of two frequencies. The frequency, which is your Larmor frequency inside your chamber, and the frequency, which is the reference signal to apply the magnetic pulses. If you're in resonance, you're at the minimum. And this is what we have measured. That's the Ramsey curve. So now you see how difficult it is to know where the minimum is, because it's high precision. So you have a lot of curves. So let's zoom in into the central fringes, and you still don't know where you are. What is now the central fringe? What is the frequency you actually measure? And that's why we do something which is having something like a co-magnetometer or a second reference measurement, and we measure relative to the second frequency measurement. And so we know where we are in these fringes. And we actually only measure in the central fringe the slope here. So this is the highest derivative, you have the highest sensitivity. And if you look at that, the sensitivity of a frequency measurement at these points is 1 over alpha. Alpha is the visibility of this fringe. So the maximum is 1. So we are close to 1. So you can't get much more sensitivity to there. T is this period, how long you wait for accumulating this phase difference, or which makes your interference pattern. The longer you wait, the better. Unfortunately, neutrons decay, so you can't wait forever. So at one point, there's an optimum, and that's one of the first steps you have to find when you do this measurement. And then square root n, that's just in any counting experiment, the number of neutrons which you can actually count. And there, obviously, you can still have much more. That's a competition since more than 40 years. Since more than 40 years, people think they can build a source which is 2-3 orders of magnitude better than what is existing. And in the end, unfortunately, most of these sources were underperforming. And we are now about where we wanted to be 30 years ago. So when you now apply an electric field, so it's the same thing, then you add these, and you kind of measure 2 of these central fringes with these 4 points, and then you take the difference, and the difference is only that now you get an extra factor of 2 times E, so you want to go to very high electric fields for highest sensitivity. At the Polshera Institute, our ultra-cold neutron source is built on the principle of what we call a super thermal source. Kent already explained you that with superfluid helium. In our case, we use solid deuterium, but I walk you through this entire very busy plot and slide one by one. So we have protons coming from the world's most powerful proton accelerator. Is something like 2.2, 2.4 megawatt of power. The entire beam is put onto a lead spallation source for 8 seconds and produces some 10 to the 18, 10 to the 19 newtons. However, they have energies up to some 200, 500 mega electron volt, and so we couldn't use them for storage or anything. They would just disappear immediately. And so what you do is you put, like in the reactor where you want to produce electricity, you put a lot of water to thermalize the neutrons. So you reduce that energy to room temperature. That's 25 milli electron volts. And then inside here, you have a solid made of deuterium, and a solid you can excite phonons. So in the first part of the lower part of the solid, you actually further have a moderation process. And at one point, they come into a range of a few milli electron volts, the neutrons, and then they can excite phonons at some milli electron volts and lose all the energy. And then they are ultra cold neutrons. Ultra cold means that you can store them inside a material bottle. So the strong force of the nucleus in your material wall is reflecting the neutron under all incident angles. And that's then used, like you can imagine that ping pong balls flying through such an empty room where it's confined by materials which are either something like diamond or nickel molybdenum or deuterated plastics. And they bounce, and they have a certain chance to actually bounce all the way to your experiment. And all this process loses neutrons. So the big challenge is that you keep as many neutrons on your path to your chamber. And so we end up here with something like 20,000, 25,000 ultra-cold neutrons at the beginning of the experiment. So they bounce down here. You see here, we have to go to a smaller diameter. You can remember that for the later part. And you put them up here into the bottle. There's something which closes that. This is the top electrode, the bottom electrode to produce the electric field. So up here, you have these ultra-cold neutrons below 350 nano electron volts, actually much lower in energy. So something like 100 nano electron volts. And then they bounce around here like ping pong balls until you open the door again. And then you empty in this last phase all the neutrons into a spin detection system. So you use a magnetic foil, which is reflecting one spin state, and to detectors below to detect the ratio of spin up to spin down neutron state. Yes, please, questions.
Question about neutrons, you cannot push them, right? So how do you push them?
Well, you don't really push them. You wait until they diffuse there. Yes, it's a kind of a random walk. You try to have as many specular reflection as possible. The rougher the surface, the higher, so to say, the resistance of the tube, and you will have many back reflections. Yeah. So you want to have highly polished tubes so that they reflect always under the same angle. And then once they are up here, the challenge is that they will also go back. Yeah. So you kind of optimize in your process this filling curve, which you see here, that's the filling, and then close the door. And this happens here. And you optimize that by experiment. And that's what we call the commissioning phase. All these things have to be measured before you actually start measuring, because you don't know a priori when this moment will be. Just ask questions whenever they come, because it will take anyway some time. So that's then sort of saying how you optimize. So essentially, I told you this: the sensitivity is 2 alpha TE square root n, and now you can optimize all of them. Down here, that's the free precession time, this T, and you kind of try to optimize your experiment using that factor to have the highest sensitivity. And here you see it's 10 to the minus 24. That's kind of astonishing, but that's a single cycle, one measurement. So once loading neutrons into your box and once emptying out. And now what you see, there are actually more factors. You have the electric field. Okay, that's pretty challenging to get it above some 11, 12, 50 kilovolts per centimeter, because you have this insulator in between the two electrodes. If you wouldn't have them, you could go to much higher electric fields. Then this alpha, that's the visibility at the end. There are two ingredients. That's alpha zero. We call that the polarization at the beginning. I said it's 100% polarized. So typically it's not. It's something around 90. In our case, it's 83% polarized in the beginning. And then you have the second thing here. This is the depolarization term. So once you have the neutrons inside your box, they will not stay perfectly polarized. There will be things which depolarize them. For example, wall collisions, but mainly magnetic fields. I will come back to that. And then you have the number of neutrons at start, that's about 20,000. And then you have something which is an exponential loss due to nuclear reaction with the wall, due to the beta decay of the neutron and other things. And so you will lose neutrons all the time. And we model that with 2 exponentials, and they just tell you that you can store them for about 180 seconds. And all that goes into these plots. And you see there, find some minimum. And so in the end, we measured around 180 seconds. Actually, here you think maybe it would have been worthwhile to go there, but that's only a few extra percent. And then there comes in another thing which is important, that's stability. So the longer one circle, the better the stability has to be, which is not part of the statistics. And I will talk about that also. Stability, that's what you see here. So if you want to go to higher sensitivity, you have to repeat the measurement. And now, very simply thought, if you have a very bad magnetic field, the Larmor frequency will change all the time, like in ABCD. And then if you want to fit the central fringe, you will get a really shitty fit. And you will lose all the sensitivity of your single cycle because the stability is not high enough. So you must make sure that it's stable. And you do that by looking at something we call the Allen deviations of stability. That's something which comes from clock characterization. So a frequency is not a priori stable neither. You have to have a huge effort. So atomic clocks are very stable, but original, for example, clocks from quartz in your computer, they only have a stability of 10 to the minus 6. So they go out of tune. And then normally today you are recalibrated every now and then by a GPS coming over your Ethernet. That's why your clock still is correct. Old people still know their clocks, which they had to wind up. They were not stable neither. And what you see here now is the stability of this delta B. And if you have perfect statistical sensitivity, you go just like a square root n law, and you get more and more stable and more sensitive. Or it's stable, and that's why you get more sensitive. Here, that's a plot from real data, and you see that after about 20 cycles, or 20 cycles, you're at the minimum, and after that, you start to increase or decrease your sensitivity because your field is drifting. And so there were 2 ideas essentially what to do about that already in the 70s. And one was in Gatchiner, build a double chamber. So you have 2 chambers which measure the same magnetic field. And the other idea was to have in the same chamber 2 species which measure the same magnetic field. And in both cases, you kind of can normalize this drift. And then you get this violet curve, which is following the statistical sensitivity. That's the spectrometer we have used for the measurement. So I walk you quickly through. I told you what the neutrons do. That's the electrode which produces the electric field. All that is set into a vacuum tank, which has about a 1 meter diameter size. And then around that, we have a mu metal shield. That's something you also heard of from Kent already or from Tito. That's essential to control your magnetic field. So this was a 4-layer magnetic field shield with a shielding factor of about 10 to the 4. In addition, we had an active coil system, which was compensating magnetic field changes from the outside. And inside here, you see something which is called the mercury lamp, and the mercury lamp for the UV laser or the UV laser. And we used mercury inside here, 199, also a spin 1/2 particle to measure the magnetic field in the same volume as the neutrons are. And so we could use that frequency to normalize the other. And in the end, what we do is we take the ratio of the neutron frequency to the mercury frequency and then use that as observable to search for an electrodipole moment. I was telling you all that. Now the mercury magneto works like that you have a resonant light, circular polarized. You have a below the precession chamber, a chamber which we call the polarization chamber. While you do the experiment up here, there are new atoms coming in there from a vapor source, and the light is shining in, and you kind of all put them in a spin-up state. Then you, after the neutrons have entered, you quickly open a small door, you let in the mercury into the main precession chamber, you do the same spin half flip as with the neutrons, different frequency just after the neutrons, and then you get something which is the oscillation pattern. You can observe that by shining resonant light through the chamber. And if the spin and the of the photon and the spin of the mercury is aligned, you have no absorption of the light. And if it's anti-aligned, you can flip the spin of the mercury. And because of this flipping of the spin of the mercury, you absorb the photon and you have less light. And so you have a modulation of light. And this is exactly the Lama frequency of mercury. And you see that here, let's just zoom in, it's the same data. And you have an envelope of about 140 seconds. That was one of the reasons why we didn't go to much longer times, because then in the end, you don't have enough signal to noise ratio. So we are here about, these numbers, we can look at them later, but that's principally not so important what we achieved as numbers. Yes, please. There.
Yeah. Can you explain again? Why mercury?
Mercury has this special feature that the light absorption, that the cross section is depending on the spin in the visible light or in the ultraviolet light. So you can use light to absorb this precession. Yes, so if the initial polarization is not 100%, this is, for example, the case for mercury, it doesn't really matter. It's just the initial signal to noise is worse. So you would like to have a biggest polarization possible to have the best signal to noise. And that's also true for the neutrons. So every time, yes, you do want to have highest possible polarization. That's what you then get. So if you would look at the frequency measured only with the neutrons, you would get a pattern like that. That's real data from our experiment. And if you then normalize with the mercury magnetometer, it's flat. And you see that also, and that's the same data in the Allen deviations. In the first case, you wouldn't even measure for more than 1,000 seconds, so 1 hour, and you would be already drifting out of the resonance in your resonance curve. But if you use then the mercury, you're actually along the sensitivity, and that's really essential. But however, this trick has also some costs. There are no free meals. And now we look at all the systematics. Well, we don't discuss them all in detail, but in principle, what you can do is you look at this ratio. So I told you we measure it as a ratio. The EDM is essentially the difference.
Sometimes.
Now it works?
Yes, we can hear you again.
Okay. Skylar, better?
Yes, still don't see anything, but I can hear you at least, and that's what's important.
I can try to reshare the.
No, the screen sharing works. It was just the audio.
The screen sharing works. All right, yeah. Good. So I continue? Is that okay or not yet?
Yeah, what's in the chat?
Yeah, just go ahead.
I have to accelerate, I realize.
Sorry. Just a second.
Maybe this one. Okay. That's better?
Yep, now we can see you too.
Hello. So
Thanks.
I need to accelerate. I see I already spent half an hour on the introduction. So the next thing, and I go into a little more detail, is what we call the Fales EDM, which is something like the geometric phase effect, which is very important to understand. Ordered motion is something which is also arising, but it's very diffuse scattering, and so we don't really care. We can discuss it if you're interested. And then there's something which is the quadratic effect, which is essential if you don't have exactly the same electric fields. All the other things here in the back, these are systematic effects which cancel if you take the difference. So if you take up here the difference, oops, Do you see that? Yeah. Then all of these cancel because they don't change sign with the electric field. But if there's a correlation, an unintended correlation with the electric field, obviously they will also give you a systematic. So you have to keep them in mind and also look at them as a channel of problem. So now this V cross E dominant systematic effect. It's the motional magnetic field, and although these neutrons are only moving at some meters per second, it still sees a relativistic field. It still sees a V cross E field. And their naive assumption is because it's stored in a chamber, they have a mean average speed of 0, so this thing is 0, but it's not the case. The thing to think about is, or how I think about it, if you look from the top, the atom, or in this case, the atom whizzes through the chamber horizontally. And I told you, if you apply a horizontal field with a correct frequency, you flip your spin in the beginning. So this was the way how you do the spin flipping. And now this atom is whizzing through the field. It sees two fields. This perpendicular field are two fields. This is the field, which is the field because of gradients. So different fields at the ring or at the outside than in this inside, plus the field coming from the electric field in this V cross E. And then you see, because it moves differently, it always oscillates. You have an oscillating field in this plane, and this drives a spin flip, or what we call, that is a Ramsey-Bloch-Sigert shift. And this Ramsey-Bloch-Sigert shift is quite important. When you move through, you can see, develop that formula B squared to something which is proportional to the gradient itself. Then you have this linear in E effect, which is the Fels effect. And then you have this quadratic effect, which is only dangerous if you have different electric fields up and down. And so in the end, what you get is this Rabi-Bloch-Sigert shift effect, because you are not on resonance, but you still kind of push all the time the precession of your mercury atoms. And this depends on this WR, which is the resonance frequency or non-resonant frequency. And this depends on how your particle goes through your chamber. If it's very slow, it's different than it's very fast. If you will have a ballistic, so that depends. And if you put all that together, then you can see here the fields such a particle would see. That's a Monte Carlo simulation, just one case to illustrate. The blue thing is the gradient field. So you're within some picoteslas, always below a nanotesla field. They see it at every trajectory in average. But the red field, this is the field which comes from the relative effect V cross E. So there we see fields which are on the order of some 3 nanotesla. So that's 3 promille of the real magnetic field we want to control. And you see that this is random, but as you only see the magnitude of that, it's not random anymore. And so you accumulate an additional phase. And if you put all numbers together, you see it's depending on the diameter of your cell. In the case, we had a 0.5 meter diameter, and this means the systematic effect is the gradient. I told you it's the gradient times 4 times 10 to the minus 27. So if you have a 3 picotesla per centimeter gradient, which is a really good field gradient, you have a larger systematic effect than you actually would have sensitivity from your statistics. So you have to control that. And the way we wanted to go was to have a cesium magnetometer array with many, many cesiums up here, which measure the field, and you can extract a gradient by doing something which we call a polynomial decomposition. I'll come to that later. However, one prerequisite that this works is that all the cesiums are accurate, and accurate enough that essentially they measure the same field if you exchange them. And this is very, very difficult to achieve and accomplish, and we didn't accomplish here. And so we only accomplished the accuracy of 8 picotesla per centimeter. So that's more than a factor 2 worse than our statistical sensitivity. So it was impossible to use it. And so we came back to something which is sometimes considered as a problem, but actually in this case, it was our way of saving the measurement. And that's something which is called the center of mass offset. So if you look now again at this R plus R minus here, you can have this degravitational, this shift. And this comes about that mercury is a thermal gas, so it averages the chamber equally, and the neutrons are not. The neutrons sag to the bottom, and so they have a center of mass offset. If you have in addition a gradient, they will see 2 different magnetic fields. So essentially what you see is a change in your R ratio -1, which is proportional to the gradient. So what you can do now is that you measure your EDM as a function of your gradient, and you measure then the R value. So you have R as the value which measures your gradient, because R is directly proportional to your gradient. So that's the statistics. So in total, we had 100 sets, a set with something like 2 days of measurement. And this means 55,000 cycles, each cycle in average 11,400 neutrons. So something like 5 million neutrons. That was a question before, I think. When we did that, now we came to the analysis and we had all that, and we measured all these sets with different gradients. These are the gradients we applied. And then we separated them in sets where we have positive and negative electric fields. So we reversed them. And then one of these subsets, which are here indicated as 0, 1, had 112 cycles. And each of them, we did the central fringe fit. So that's this cosine curve of the central fit. And you see here many points. The faint one are the ones which indicates a blinding. So if you have a blinding, you see that the entire curve shifts. That's what we did in addition. But the unblinded version you can see here. And what we do is we fit then this curve for the 112 cycles. And then we actually invert that fit and solve it for the frequency for each individual cycle. And what we have to do then is that we do that with a full correlation matrix, because certain values are correlated. And then we take for each individual cycle the ratio R, and then we kind of move from this big change in case of the neutron alone to a case where it's flat. And then we can really start looking for the EDM value. Yes, please.
The functional form we use is unique, or is theoretically motivated to the functional form of the fit.
Well, it's the functional form of the fit is theoretical motivated from the Ramsey pattern. You can calculate that analytically. And then you can show that at the current statistics, central fringe is sufficient to calculate that with a cosine with the adapted width. So
That's why I spoke to some likely given frequency for the outer.
yes, but we don't measure at the outer. We measure only in the central fringe.
Oh,
We don't take the entire Ramsey. We would be very inefficient, because the sensitivity decreases whenever you are at the apex of your curve, and it decreases at the fringes. So you want to measure only in the center.
why don't you take, why don't you just take the parabola and stick to the video also?
Well, you could. Well, one could do many other things. True. One could have also a phase shift, and then you only have a slope. So there are many things to do. We did it like that, but we can discuss whether we looked at all the other things. They are not more sensitive. So in the end, it's just. So what you do next then is that you get all these ratios, and essentially what you then see here is a step in this function. This step is the electric dipole moment, and it's not surprising that you see that, because we had blinded data and you had some electric dipole moment in there. And so you do this fit because although you normalize your data with the other frequency, there are still frequency shifts in both systems coming from certain things. And so by doing this fit, you remove this slow drifts, and then only the step function, this is this alpha A here in this fit function, is then proportional to the EDM. And then you, in the end, you get your EDMs for each cycle. And so we had a statistical sensitivity. We could say that already before we started unblinding of 1 × 10⁻26. Now, systematics effects. I told you there is this problem with the fails EDM, and this is essentially these two cases in our publication, which is the higher order gradients spoiling your direct linear term in the ratio, and something which is called the transverse field. So I told you already that this gradient is essentially proportional to G1, 0, and we wanted to measure it like that. However, this is not the full story. you also have all higher orders in there, all uneven higher orders of the magnetic field. You will also see them in this gradient shift here. And that's also true for the systematic effect, which is this fails EDM, this motional. There we also have these higher order effects. And so what we can now do is that a part of that is canceled, and the other part we have to measure. And the part we have to measure we call phantom modes, but that's just some linguistic way of talking about stuff. We did that by removing everything from the chamber. These things which were removed were all characterized in Berlin, so we know they were not contaminated with magnetic things. And we moved this mapper, which has a magnetic field sensor here, up and down, and recorded magnetic field maps like that. What we did then, you can assume that there is no magnetic field source in there, no currents, no other things. And then you can do a harmonic polynomial fit to them and get kind of a set of polynomials with certain coefficients, which are then GL0 minus 1, for example, or here G1, 0, which is the linear gradient. And then we have all these gradients and can calculate these other effects. And we did that using this decomposition with a field mapper. When you then come back, you correct now each of these points for these additional fields. And then what remains is a linear dependency on R. This is this kind of effective linear gradient, which is identical in the fails EDM and in the gradient offset. And then you get a line fit, and where the line crosses, that's where your real EDM is. And what's the real EDM is 6 times 10 to the minus 6. So also not surprising, it's still blinded. What we did is that we did all that independently in 2 analysis groups and worked on it until it was identical in statistics, meaning the arrow and chi-square statistics. As a cross-check, the slope is proportional to the center of mass offset. You remember that there was this delta Z times the gradient. And so we could extract that too, and we could measure that also with other ways, and that was also in accordance. And in addition, this central value here is in accordance with the literature value of the ratio. When you don't have any additional magnetic gradients, then you measure essentially the gyromagnetic ratio of the neutron to the mercury, and that's also in accordance. So we had several cross-checks that we are actually at the right point. We only now knew there's something which is still missing, that's the unblinding. Maybe I skip these things because it takes time, and I want to go to the second part. And then we unblinded, and we had 2 blindings. So we had the first blinding, which was for everybody the same, and the second blinding was different for the 2 groups. So when we removed the first blinding, we knew that we were in principle good. And then we fixed the rest of the paper, fixed everything, and then unblinded, put the number into the paper, and published. And so the mean value between the 2 was the 0 times 10 to the minus 26 plus minus 1.1 for statistics. And then systematics were 0.2, which is a factor more than a factor 5 better than the previous best experiment. All that happened between 2017 and 2020. And this led to a new point down here. We are very proud of that one. And this was all done with a big collaboration, but I will come back to that. So now maybe there's time for questions on the analysis and all that. And then I go quickly through what happened since.
Can you go to the previous slide?
Pardon?
To the previous slide, I think.
So
the red one is the projection.
Yeah, the red one is the projection. That's the future. That's what I will talk now in the rest of my 10 remaining minutes. Any questions so far? No? I'll have a little water for my voice. Oops. So the sort of natural upgrade was to combine the 2 ideas of the 70s, which was the co-magnetometer and the 2 chambers, into one experiment. We are not the only one who thought about this, so it's not unique to us. And so finally, we wanted to wrote something 2 years ago, which is, or 1 year ago, which is a technical design report of the entire experiment. So everything I tell you now is more or less described in there. You can read it, and I just put some highlights together. So the experiment, you will re-identify this thing. This is the ultra-cold neutron source. These are again these guides. Now you see maybe better how long they are. That's 12 meters. And now what is a big difference is that you don't have this retraction anymore. You don't reduce your guide diameter, but you go essentially with your full guide diameter into the chamber. And what you also see is we go in a small step upwards and not like in the other experiments, 2 meters nearly. So all that leads to higher statistics. And then we have in here, and you can't see that very well, but I have other pictures, the 2 chambers, an upper one, a lower one. In the center, the high voltage electrode, and all around we have things to control magnetic fields. And that's happened between 2017 and 2020, and you can follow up in the movie. All experimenters already gone. We had to do then some groundwork. So there's a new basement here, essentially a base plate which was produced, which is isolated from the rest of the building to have reduced vibrations. Then we have 4 very nice granite pillars, also to reduce vibrations. And on top of that, we then set up a support for the magnetic shielded room. That's an access platform, so we can actually work inside the room and build it. Now you have the scaffolding, and now we started setting up the room. So before that, we actually characterized the entire room magnetically. So we knew exactly the same field, the field of every point in the space. The door was mounted first. That's also awkward, probably. But that was now the outer shell. And next, we mounted the inner shell. So we built the house from the outside inside. And this is now a thermal insulation, a wooden house, all made of wood to be non-magnetic. And then we mounted inside the rest of the shield. So let's look at the shielded room. So essentially, it's a 2 + 4 layer magnetic shield. So we have an outer room, which has 2 layers. Then we have a large in-between space where we can have electronics and things like that. And then we have an inner room with 4 layers to accomplish the shielding factor, which should have been or should be something like 100,000. We measured that once it was set up. All of them axes, so it's X, Y, Z. Inside the room, they have a shielding factor at below 0.1 millihertz excitation frequency of 100,000. So that means that you have an outside coil with exciting a field, and you look inside what is how much of this amplitude you still see. And then you see that up here, the sensors don't see anything anymore because it's inside the noise floor of the sensors. And this was our specification. So we are very happy with our shield. And then we continued. Next thing is shielding factor, then remnant field. So the field you have inside when you measure the field magnitude. And here what we have seen is that we are typically within a 90% confidence level below 100 picotesla for all points. The scale here is from the center to the floor, to the surface of the mu metal. And so the experiment will be in the central 1 meter here. And in this range, it's everywhere good except towards the door. And that's kind of expected because the door you have to open and close. And so it's not one layer of magnetic material or magnetic shield, but you have to push against it. And so it depends a little bit on how good you can actually magnetize it. So we have a remnant field in the central cubic meter or 8 cubic meters where we will mount the experiment of below 100 picotesla and with gradients which are also very, very small already. Then we converge to a design of the chamber. These are 2 chambers, a top one and a bottom one. In between, you have the high voltage electrode, which is charged up to something like 180 kilovolts, which results in the 15 kilovolts per centimeter field. Outside here, this thing here is a cage. So to make sure it's a Faraday cage, that everything which is outside there is at ground potential and don't see the high electric field. And then you see down here and up here, these blue balls. These are cesium magnetometers. So in total, we have 112 cesium magnetometer, which locally measure the field. And we put enormous effort to have an accuracy, which is below 2 picotesla, to accomplish a correct decomposition of the field to assess all the gradients correctly. That's just another image. And here, remarkably, you see this kind of grid. That's 55 kilometers of cables in 8 coils. And that's our new active compensating magnetic shield. So how it works is that we have close in a 1 centimeter distance around the magnetic shield. We have field sensors, and whenever they see a difference, we adapt all the currents in these coils accordingly so that the shield itself never sees a change of a magnetic field more than 1 microtesla. And so it stays very stable, and the inside field stays also very stable. So that's a measure of stability. Then you see here the now mounted inside coil system. So this is the door, and you see all these wires. And all these wires, they're equidistantly spaced. They produce essentially a solenoid field. And it's optimized up here with Lamé coil system, and plus the magnetic shield, it produces an extremely homogeneous magnetic field already. In addition to this 1 microtesla field, you see here, it's extremely difficult to see on some rectangular coils. There are 56 rectangular coils on all the surfaces, and these are used and can be used to adapt the magnetic field to optimize the uniformity. In addition, you remember that we had this issue with the Fels effect, which are proportional to these G10, G20, G30 field gradients. And so what we have is dedicated coils to actually adjust them and manipulate them and measure things as a function of these gradients. Now we have mounted the vacuum tank. It's vacuum cleaned in that case here. It's about 1.80 meters in this direction, 1.80 meters in this direction. And it's just being mounted and now in the last months characterized magnetically. The expected performance, we can go through the numbers. The main change is that we are now having something like 130,000 UCNs per measurement. The rest of the numbers were kept similar as before. We accomplished in the old experiment already fields of 15 kilovolts per centimeter, so we are confident to do that again. And then you see here that we will just about, after 500 days of measurement, reach the 1 × 10⁻27 sensitivity. A 2 sigma sensitivity would be, or limit would then be 2 × 10⁻27, something like that. And that's planned for the next 5 years.
Sorry.
Yes.
You explained a lot about the control of the gradient of the
yes.
field. But then you say that one of the biggest improvements compared with the previous experiment is actually the statistics.
Yes, but yes, you first have to improve the statistics, otherwise it's not worthwhile to improve the systematics. Sure. But at the moment we had systematics on the level of 2 × 10⁻27. So if we keep it as on the same level of control, we won't improve much. We will have the same statistics. So we want to be a factor 10 about better in statistics, systematics than in statistics.
Right.
So you
can improve the statistics, but in order to make that really effective, you actually need to.
Yes. Yeah. This is pure statistic, but to actually profit from them, you have to improve the systematics accordingly, and that's why all the effort goes into magnetic field comprehension. There's also some effort to have more neutrons, sure. Yes, so the plan is then, so I told you that will measure, or we measured before this crossing line, we will do something very similar. Now we have the advantage that the center of mass offset on the top and on the bottom is nearly canceling, but there's still a tiny offset of about 0.1 millimeter, and that we can then use again to use this extrapolation with a very well controlled effective gradient. And then for that purpose, we have to understand fields like that. That's now this phantom mode. This is what I told you already. This is the cubic gradient inside the chamber. It's essentially symmetric, but it produces a large electric dipole moment, which you don't see in the ratio of the frequencies, because the ratio of the frequency stays the same. And so you have to measure that with some additional tools. And that's the way how we measure it, is to have these 112 cesium sensors. And the idea is then that we can measure the G30. We sometimes call it G tilde. That's an effective linear gradient, because the geometry of your chamber is known. You can kind of calculate an effective linear gradient. But essentially what we want to need is something like 80 attotesla per centimeter, per cubic centimeter. So that's extreme challenging. And we tried how to place all these sensors. And essentially this requirement we want to meet was this green line. And we had an accuracy of 2 picotesla of each sensor measurement. And you see, if you just kind of symmetrically, naively put them, you're not sure that you actually meet your requirement. And what we then had was a student who did a kind of a machine learning algorithm, a genetic algorithm for placing these coils, these bulbs, optimal in the magnetic field to have highest sensitivity. And that's then the final result down here. So now with the 2 picotesla accuracy we accomplished, we will be sufficiently good to actually correct all these effects at the level we need. All these extreme requirements need verification. We do that in Berlin. So you see here kind of a field map of how good stuff has to be non-magnetic. So this is the scale of being non-magnetic. This is the central upper chamber. On the bottom, it's essentially symmetric. And you see here, these are very small fields of a nanoamp per square centimeter. This means something like a few picotesla in a 5 centimeter distance measurement. And we measure that with the squid systems. You see here the squid system. We see here a part of the aluminum tank, and this is up here. So this should be smaller than the 500 nanoamps per square meter, which corresponds again to some nanotesla in 5 centimeter distance. Down here we see the support, and here we see the supports for the cesiums where we mount the cesiums actually. And so all of these things, all parts, even the 55 kilometers of cable were tested in Berlin under the squid system. The magic field option, that's something for the future. I won't talk about that today. If you have questions, ask someone of this perfect collaboration or me. I was very proud to be a long time, for 4 years, the spokesperson of that collaboration. It's a great team, very nice people to work with. And I'm proud that we had published finally this very stringent limit. Thank you very much for your attention.
Questions from the audience, from Zoom? Oh yes, sorry.
So, Philip, nice talk. Thank you. So, in the last few years, I've been, maybe you can tell from my talk, thinking about the systematics that occur within the free precession time. So, in your early results, when you show the Mercury precession, if you fit that all Fourier transform, you're kind of slightly weighted towards the shorter time because that you have higher signal amplitude. Whereas for the neutrons average precession frequency, I'm trying to think of the weighting because you preferentially detect the lower energy UCNs. So there's not a single frequency, and then also for the gravitational offset within that 100 seconds, it's changing because of spectral differences. And similarly in the double cell, you're going to get different evolutions of that. So can you comment on your thoughts on that?
Well, we only can measure the ones which survive. So I don't really care about the spectral shaping because the ones which die inside the cell, I won't make it to my frequency measurement. So I'm only concerned about that. So it's only the accumulated phase which is relevant for the measurement. And that's true both for the mercury as for the neutrons.
Oh, I thought the mercury you're seeing it.
Yes, but in the end, you use the weighting, correct weighting of your thing, and so you get the correctly weighted frequency.
But for the neutrons, you're preferentially seeing a low energy one.
That's why you have the center of mass offset. The ones which start high and are lost are gone. So you don't measure their frequency anymore.
So is that the offset difference between the two changes?
Exactly.
Okay. But that's based on simulation?
That's based on simulation, but we will measure it. It's probably something like a year of measurements until we know all these numbers from experiment, and then we can draw again this optimization curve and know how to operate the instrument perfectly. So that's something which has to go still there. At the moment, we are based on the simulations, yes.
Any more questions? There is one there. Oh, yes.
It doesn't let me down, good.
Skylar, please go ahead. Can you?
Yeah, thanks. And thanks, Philip, for a really impressive and well-presented overview. I'm again sorry that I can't be there in person, and we'll have to find a time to sit down over a beer and really go into detail. So I'll confine myself to one point or so. You mentioned that you're now filling the neutrons from a height much closer to the output of the source, and this obviously delivers you higher statistics, but at the cost of shifted energy spectrum. And can you maybe discuss a little bit that balance between the statistics and the systematics and the holding time? If I did my back of the envelope correct, then you get something like a 50% increase in the delivered density for your statistics table. And I guess that has to be somehow compromised with a harder UCN spectrum coming out of the source at the lower height.
Well, essentially, what we did is that we characterized the entire beamlines, the source, the storage properties as a function of height at the second beam channel, West 1. And as we can describe that perfectly in our Monte Carlos, we use that input to optimize the position of the second chamber or the two chambers relative to the south beamline. So that was an optimization in Monte Carlo, and it's optimizing statistics to first order, because the delta H offsets as it essentially cancels, because you have the higher one and the lower one, and you take the difference of the two. It actually cancels again, because you then can even change the polarity of your electric field, and you have a second cancellation. So you're extremely unsensitive to that systematic. It's actually something we think it's important to keep that, because it's a control handle on measuring the effective gradient, because the R ratio depends on this effective gradient. If Z would be identical, we would be blind to that. But we are pretty sure not blind to that. And so the delta Z is essentially something which is a coincidence, which is very helpful to measure a systematic effect. It's not something you want to avoid.
So roughly how much higher in energy is the mean UCN in your now lower experiment?
Well, the difference in height is 0.1 millimeter. So the energy spectrum, the mean is a few nanoelectron volt difference.
Okay.
So there was also the idea, but that's also not really reasonable. You could, like, the lower one has a lower spectrum. And so what you could do is that you actually put the detection system such that this lower spectrum is cut away, and you can't detect it. And then you would kind of detect the same spectrum, but not really, because also the spectral forming will be different. So I think we just characterize it correctly and then correct for that. I think it's always better to see systematics than not to see them.
No question.
When we've done this paper together, and I noticed that at Los Alamos a lot, when we run the source, the solid deuterium crystal conditions, if it's slightly frosty, and over time we get a lot of spectrum changes as well. So, I mean, so if you do separate systematic studies, you know, spin echo and all that, how do you guarantee that you have the same spectrum at a specific fill and empty?
Well, as I say, the spectrum is changing. Yes, that's true. The spectrum is changing over days.
Yes.
We now have new methods for optimization of our source. So all this doesn't go into here. So we had a huge effort and program to better understand the source, have a higher output, and the kind of reconditioning of the solid deuterium is also something which is done more or less online in the future. So it's not degrading anymore as much as before. But even then, if you have you kind of have to optimize the rhythm, how often you change your electric field, how often you change things. And these parameters go into that. So you measure and characterize, that's commissioning, and then you know, and then by changing and canceling, if you measure positive charge electrode to negative charge electrode, take the difference, essentially all this effect cancel. And you're left only by how much is the drift between these 2 points where you cancel. And if that's relative short, it's very small.
So I have the $1 million questions. What's the timeline?
So I kind of stress that we need a commissioning time. So I think we work hard that this year we have first neutrons in our system. We won't do any spin gymnastic, how we call it. So we don't start spin. That's probably next spring that we are ready for having apply pulses and do some spin physics. And then it will take about a year. This would then be 2023 to characterize everything and know the parameters, how to operate optimally. And then 2024, one could imagine to start data taking. And then I said we need something for this final statistics, 500 days. We typically get something like 180 days a year. So it could be 3 years, but that means everything always works perfectly. And there are so many systems which are reliable to 90%. So if you have 90 to the power of 5, you suddenly know that this is not such a big number anymore. And so it could take much longer than in the most optimistic scenarios, but a new number is probably likely after 1 year of data taking, that students start analyzing, that they know what it's about, that we have an idea where we go, and that could be a number which is already in sensitivity below 10 to the minus 26, but probably in the limit still above.
So let's say first number 2025 and we'll
you said that. Yes.
Okay. Okay.
Yes.
Thanks.
I used to be, I'm not anymore spokesperson, so I don't give dates.
No, that's fine. Yeah. Thanks. Are there more questions from Zoom? Okay, if not, let's thank Philip again.
Thank you.